All right, welcome everyone. Today I'm joined by Matt from Physically Debunked, and we're going to be talking about the fine-tuning argument. So this is the first, I guess, collaborative video I've done on my channel. Oh no, I guess I've done a couple with Nathan, but first with other people. So welcome, Matt. Do you want to say a little bit about your background and what you do on your channel?
Yeah, no, thank you very much for having me. So I'm currently in my first year doing a PhD in early universe cosmology. Specifically, I'm working on various features of inflation. Even more specifically, I'm looking at the formation of black holes in the very early universe and gravitational waves as products of inflation and as products of various general classes of models of inflation. But yeah, I'm 9 months in. I've done it all from home. I haven't gone into the department once, thanks to COVID. So it's been a strange experience, but it's very, very interesting.
So that whiteboard is in your house?
Yes.
It's a big whiteboard.
Well, I actually have two YouTube channels now. There's Physically Debunked, which is very much about looking at science, looking at physics, and looking at atheism and theological arguments through the lens of the physics and science that I know, and trying to discuss whether the arguments that theists propose, how plausible they are in light of science. And then my other channel, which is called Shots in the Quark, which is why I bought this whiteboard, is purely about philosophy of physics. I studied physics and philosophy at university, so I had a really nice grounding in the crossover subject, which is the philosophy of physics. And I think it's absolutely fascinating and not something that many people encounter, even if they'd end up doing a physics degree, some of the ideas that are included in there. So on that channel, I'm talking about philosophy of space, philosophy of time, philosophy of quantum mechanics, and that's why the whiteboard's useful. But yeah, my girlfriend's pretty annoyed because it takes up a lot of space in the bedroom, which is where I am.
Yeah, I've been reading a lot about interpretations of quantum mechanics and ontologies of quantum field theory recently, so we might have to do another episode on those at some point.
It's a very interesting area, fascinating stuff.
All right, well, let's start talking about the fine-tuning argument. So we sort of, hang on, if I can bring this up here, let's see if I can get this to work. Yeah, so there's this paper here that was written it's actually nearly 10 years ago now.
A decade ago now, isn't it?
Yeah.
It's old.
Time flies. By Luke Barnes, whom I debated a few weeks ago now about the fine-tuning argument, and he he mentioned this paper a couple of times during the discussion. So I thought it would be good to have a sort of a follow-up discussion here with Matt about this. I didn't actually know about this paper at the time I debated Luke, which is I guess my fault. I did know that he'd written a book, but his book's at a much more popular level than this. This is a very technical paper. But there is, can you see that here? Yeah, I'll just zoom in a little bit. It does provide a good overview of some of the extant literature. I guess it's maybe slightly out of date, but in general terms, I think it's going to be applicable. And the different, I guess, cases of fine-tuning that it talks about. So we might refer to this a little bit. We might not so much. I'm not sure, but at least I thought I'd mention it, and maybe we can start by looking at some of the aspects of the contents page. So there's sort of a few different aspects to the fine-tuning argument. Maybe I'll bring us up here. Oh, no, I'll leave that for the moment. So one would be, is the universe fine-tuned for intelligent life? And then the second would be how to account for fine-tuning, so explanations of fine-tuning. And the two main approaches to explaining fine-tuning would be multiverse theories and theistic theories. And so that's why here in this paper you see that section 4 is covering basically evidence of fine-tuning, and then section 5 is discussing the multiverse, because that's the main competitor to theism as an explanation. Now in this particular paper here, Luke Barnes doesn't actually talk about theism apart from like a sentence at the start and at the end or something like that. But I mean, it's sort of clear that that's the gist of the paper, even though that's not really presented as a competing hypothesis. But anyway, so I think it would be good to start with the first of the two questions, and then we can move towards talking about explanations of fine-tuning. So hopefully this will be interesting, because maybe I'll bring us up and then I'll bring that paper back if we need to. because I have a fairly unpopular view in a lot of circles, which is I'm not convinced that it's been established that the universe is fine-tuned for intelligent life or for embodied intelligent life. And I discussed this a little bit in my book, although I think that the discussion there could do with a bit of fleshing out. But the fundamental objection, and I raised this in the discussion with Luke, is that we don't know what the necessary or sufficient, or even have a close idea of what the conditions would are needed to have intelligent embodied life. And so I don't know how we can make the claim that we know that the universe is fine-tuned for such life. Now, when I asked Luke about this in debate, well, his first response was to say, well, he's a physicist and it's his job to know these things, which I thought was rather unhelpful. I mean, we did go into discuss it a bit more, but anyway, so Matt, on the basis of your knowledge and also maybe some of the stuff discussed in this paper, what are your thoughts? Do you think the universe is fine-tuned, and if so, how can we know that?
So it's probably useful to start with what Luke's definition of fine-tuning actually is, and he has a nice, right at the start of the paper, he has a nice, precise definition of what he means by it. He says that in a set of possible physics, the subset.
Sorry, what paper is that in? Let's bring that up.
It's the paper that we have. It's it's very early on. It's basically right after it's the second page after the contents page. Right at the top. FT. Yeah, there we go. He says, in a set of possible physics, the subset that permit the evolution of life is very small. And I think that this paper and all the literature and the research that's been done in this particular area, I think is very strongly in favor of this conclusion, that at the very least, a subset of all the possible values of the constants and possible laws and things that we can have, the subset that permits the evolution of life seems to be very, very small. And I think that fine-tuning in that sense is very well supported by the evidence. And I think Barnes is right when in this paper he lays out the evidence in favor of this definition. What I disagree with in the context of theistic arguments and a theist's attempt to use fine-tuning as an argument for the existence of God, I think the problem you have is trying to get from this definition of fine-tuning to one which says that a universe in which intelligent life exists is very unlikely. And that's a bridge that Barnes doesn't really try to gap here. But the point is that there just being a small subset of the parameter space that allows intelligent life doesn't necessarily mean that the existence of a universe with intelligent life is is similarly small. You have to have a probability distribution over your parameter space, and that tells you the probability that certain values in the parameter space hold. And none of this paper, there's a couple of paragraphs maybe that very briefly touch upon this issue, but this isn't Barnes's target at all. He's just going for there's a small subset of the parameter space that allows intelligent life. But what I think is much more important for theistic arguments is that this universe, the existence of intelligent life, should be really, really unlikely, and that's evidence for God. If it were the case that a universe such as ours was exceptionally unlikely and there was only one universe in existence, then I think the theistic argument gets off the ground. But what I disagree with is that we have any idea how to put a probability distribution over these values of constants. And certainly in this paper, Barnes doesn't go into too much detail on how this could even be done.
Yeah, that is another avenue of attack that has been made against these arguments. And you're right, Barnes doesn't really talk about that here. I think what we'll do is we'll start by talking just about in parameter space, and then we can move towards talking about how to apply a probability distribution over that, and then maybe we can move then to trying to explain fine-tuning. This is one of the few places where he doesn't even use the word God. He says a transcendent personal creator, which is interesting. But anyway, So what was I going to say about that? Oh, yeah. So one thing I wanted to mention at the outset, I don't think he talks about it in this paper, at least I don't recall seeing it, but usually in this, in the articulation of the fine-tuning argument these days, when the discussion is made about possible in this context, well, as far as I understand, Luke Barnes is referring to epistemically possible, because we don't know. Well, obviously, physically possible doesn't make sense because we're talking about different laws of physics, but we don't know what is metaphysically possible. It could be that there's only one metaphysically possible universe, but regardless of that fact, as far as we know, the constants could be different because we have to discover them empirically. And so this is an epistemic possibility argument, not necessarily a metaphysical possibility. Is that how you've understood this?
That whole thing is a whole can of worms of its own. What do you mean by possible? And I think what he or the definition you have to take, based on how little we know about the universe at its fundamental level, is that this is just an epistemic possibility. We, in principle, based on the laws of physics that we currently know, we can just vary these constants within particular ranges, and there's nothing to say we can't. But most, and this is kind of why I don't like the fine-tuning argument so much, is that I think most physicists are pretty certain that if we dig deeper, we'll end up with good reasons for why these parameters can't be varied as much as we're doing at the moment. But we really know so little about what it even means to vary a parameter, whether it's metaphysically possible, whether physically possible, although that's a bit weird.
Well, physical and what's but
at the moment, all we know at the moment is that it's epistemically possible. We can, in principle, do it without violating anything we currently know.
Yeah, it is interesting there, because if you say, well, what is it? It seems to depend on what information you're conditioning on. So if you want to say, is it possible that I don't know, the mass of the top quark? Oh, that's a weird example to use. The mass of the up quark is I was thinking up, but I said top. The mass of the quarks is different to is some value, which is very different to what we actually observe. Well, it seems that it's not possible because we don't observe it, right? Or at least it's very unlikely given the information that we have, if you condition on the information we have. But if you just condition on like the laws of nature being what they are, then there's no restriction on what it can be, or at least within certain bounds. So I think the probabilities, I mean, this goes back to your point, is the probabilities here get a bit tricky, or the nature of the possibility you're talking about. Like, all things considered, the constants can't be anything. They're pretty tightly constrained by the evidence we have. So you could say, well, that could be an argument for them being metaphysically necessary, or you could say, well, as far as we know, they could have been anything. So they could, you could argue it either way, depending on what your views of modality are.
We've only ever seen these constants take a very particular value. So
yeah, exactly.
Your prior you could easily make the case that your prior probability for the value that these take is 1 for the current value that they take, and then there's no fine-tuning argument.
Or at least over the experimental range of accuracy. But yeah, exactly. So that's I think that's an interesting avenue, but I want to put that to the side for the moment and just look at and just imagine that they could be anything within the range that we're talking about here, and talk about parameter space and ask what we can say about what parts of parameter space could potentially be life permitting. So I'm just going to maybe again scroll through here, but this is a list of some of the parameters that he's talking about. I think it's slightly different to lists that I've shown before. But well, maybe is there any? Excuse me. Do you want to say any general? Do you want to make any general remarks about any of these before? Because I wanted to look in more detail about the cosmological constant, because that's one that came up during the debate. Also, the mass of the quarks, because that's an important one. I think there was one more. Oh yeah, the amplitude of fluctuations was another one that he discusses in more detail. So some of these are particularly important. There's obviously many others. Anything else you wanted to highlight there before we look at some specifics?
I mean, the first 3 are kind of irrelevant, because you can set their value to whatever you want them to be. They're things like the speed of light, the gravitational constant, the Planck constant are constants that you can make an argument that they don't really exist. They're only numbers because we use strange units of measurement. So that's
yes,
why
I don't actually know why they're included here.
Yeah,
because he doesn't really discuss them.
They're usually
reason.
included in tables of fundamental constants, but they don't appear in any discussions of fine tuning, so to speak, because they're not fine tuned. People realize they're not fine tuned parameters. They're more artifacts of how we choose to measure things. But the other things you mentioned, things like mass of the quarks, massive particles of fundamental particles, those are parameters that, as far as we know, we can just vary, because what determines them, as far as I know, are just numerical constants that are put into. Now I can share it. Here's a Lagrangian. This is the first part of the standard model Lagrangian, and something like this GS here is just a coupling constant. And things like masses, things like strengths of forces depend on these coupling constants. And essentially, these are the things that we can just vary. There aren't any constraints. There aren't rigid constraints on the values that they can take within a certain large range. And it's the values of these which we can vary. And then this varies things like the massive up and down, massive quarks, and all sorts. So those things are important. And yeah, in terms of epistemics, those are the things that we can vary and ask what happens.
All right, so let's keep scrolling then. We're not going to talk about Victor Stenger so much. Yeah, he mentions briefly this idea that the laws of nature themselves might be fine-tuned, but this is something else I've also thought about, that we have even less ability to say what the universe could be like if the laws of nature themselves were different, like the actual laws of physics.
Yeah, all these fine-tuning arguments are very much taking the laws of physics we currently know and changing parameters within them. Asking what potential laws you could have is something even more difficult to answer.
Yeah, I'm just trying to find what he says about that. Oh yeah, so he gives here it is. He gives a few examples of what problems would occur if there were different laws. Although many of these are just sort of flipping things, like making electrons bosons rather than fermions, which it doesn't really matter. A different type of particle, basically. Making gravity repulsive rather than attractive, making the strong force long rather than short range, which don't really seem to. I mean, obviously they would make a big difference, but in the scheme of changing laws of physics, those don't seem to be very big changes to me, given all of the possible things that you could do. I mean, it's not even clear what the restrictions are there. So I'm just trying to see. Yeah, here it is. He says it's not clear how such a fine-tuning case could be formalized, whatever its intuitive appeal that is, with respect to the laws of physics themselves. Just because, like, it's not clear what the spaces would even look like. Now, one thing I've been thinking about here, and I'd be interested to hear your reaction, is does it make sense to separate the physical constants from the laws of nature? Now, in terms of like the way physicists usually thinking about it, I mean, it does, right? Because there are these values that they put into the equations and then they measure them. So as they think of them separately. But I think that whether that really makes sense at a more fundamental level kind of depends on your philosophy of physics. So suppose that you're an instrumentalist, right? And you don't actually think these equations necessarily describe like the underlying reality or whatever that is, that they're just sort of predictive tools. Then to say that we're going to take the parameters that we've sort of fitted a model to and change them without changing the model, it doesn't seem to make a lot of sense to me. That's like if we fit a curve through a bunch of points and then we change, like it's a fifth order polynomial or whatever, and then we change the coefficients but keep the fifth order polynomial. Like, why would you do that? It just doesn't really make sense. The model is the form plus the constants. It's not one without the other, if you see what I'm saying.
Yeah.
What do you think about that idea?
On a philosophy that's purely instrumentalist, I think it does seem to, the idea of changing the constants in the theories that you've made up from looking at observations kind of doesn't make much sense, because changing your theory just means it no longer predicts the world, it doesn't make much sense in that respect. what I guess what's kind of underlying all these considerations is a much more realist interpretation of science and of physics, and then you do start to encounter, well, why aren't these constants other values? Now, for practical purposes, it makes sense that these constants are there because all the theories that we have and that we work with aren't grand unified theories. They aren't theories of everything. They are low energy limits of whatever we think ultimately describes physical reality. And so because they're low level limits, you're necessarily leaving out information, and you end up with constants which you can't predict using the theory and that can only be determined by experimental means. And so, I mean, who knows how long this could go on for? Theoretically, this could go on forever. Perhaps we'll always have constants that we don't know why they're there and why they take the values that they do. But the hope really is that the constants that we're talking about in the moment in these kinds of papers will be determined by a slightly higher energy level theory. And so when we know this higher energy level theory, we'll say, oh, well, it couldn't have been any different. So one attempt to try and do this is in things like supersymmetry. Supersymmetry is looking less and less likely by the day, really. But the original motivation for it was that you have all these constants which the standard model doesn't predict. Well, what supersymmetry does is it shows you how these constants attain the values that they do, and that they occur in very specific ratios. And they do that because of the supersymmetry is broken, and this is the low energy theory that we've been left with. And so in that sense, a higher energy theory explains the values of the low energy constants that appear in your theory. But extrapolating that well into the future, will we end up with a theory with no free parameters? It seems difficult. If that were the case, then fine-tuning goes out the window in this sense that we're discussing, because there are no longer things to tune. But at the same time, it's also very difficult to picture how this theory would look like. But that could just be that we're so far from it, not that it doesn't exist.
Yeah, well, and in general, people like Luke mentions this at some point in this paper. I can't remember where it is, but also in other places, they'll typically say, well, look, even if some of these fine-tuning examples are explained as necessary results of higher energy physics, which then, the symmetry breaking or whatever happens, then they'll just say, well, but those higher order properties or phenomena, whatever it is, themselves had to be fine-tuned in order to deliver that outcome. So Luke talks about that gives an example of that in terms of cosmic inflation, which we'll talk a bit more later on, because that came up in the debate with Luke as well. So I'd like to cover that. But just as a general point, I think it is interesting, because it's sort of like, I mean, suppose you did have a theory that had no free parameters. It seems like the theist could just say, well, what are the odds that would be the theory that describes the universe? Unless you can prove that is somehow the only consistent theory, which seems, I don't know, pretty unlikely.
It seems pretty unlikely. I mean,
then,
a square is a consistent theory.
Yeah.
What it's saying. It's like, I mean, but this raises...
Yeah. Sorry.
It raises fascinating questions about what it means, what mathematical consistency could mean physically, and what relations consistency has to the way the physical world is. Yeah,
but I mean, so the point is, it's not even clear to me that it's a question of how many free parameters there are, because the argument can and is still pressed, even if there are fewer, or even if, I guess, hypothetically there were none. So that is interesting in itself. I don't know whether something tells me that that's a weakness of the argument. That's probably just my bias speaking. I don't know, but it feels like it's maybe something's gone wrong if the argument kind of never fails, if you see what I mean.
Yeah, I see what you mean.
But that's more of an intuition than a rigorous point there. I need to think about that more.
I mean, anyway, these things are so far beyond the kind of levels of physics and understanding we have of the world that, I mean, anyone could say anything about these things, and you can't really deny what they're saying. Who knows? It's like, if you think that we're going to get there and there's no tunable parameters, sure, could be the case, could not be. We have no idea. So
Yeah, well, and so actually, I brought that point up. Well, a similar point that there's so much that's unknown about a lot of these topics, and I want to mention more examples later. But and Luke Barnes's point was basically just to say, well, look, we should. The arguments are based on the best current physics that we have at the moment, and so it might change later. But this is what we have currently. Now, I don't remember how much I pushed back against that at the time, but I don't think that it's a very satisfactory answer, because you should, in my opinion, you should tailor your confidence in a conclusion to how confident you can reasonably be that the current evidence is sufficient to draw that conclusion. And if we know that there are lots of problems with our extant physics, which we do, especially when we get to these sort of fine-tuning discussions and parameter space and so on, then I think that we should be extremely reticent to make any particular conclusions about what we know there.
I think you're absolutely right there. I think Barnes has a point in so much as it's fair enough to take the physics that we do know and work out what its consequences are, but then inferring from, because we know that the current theories we have break down in certain environments. We know that there's much more to be discovered than we're currently aware of. And so it seems unwise to start making big conclusions about fine tuning when there's so much we don't know.
Yeah, well, I mean, so suppose one granted that fine-tuning provides evidence for theism, but the fine-tuning proponents often like to point out the very high probabilities involved, and you've raised an objection there about how those probabilities are calculated. We'll come back to that, but the point is, irrespective of that, then you would have to weight, or it seems to me that you should weight the strength of the argument or those probabilities against how confident we can be that all of the relevant physics is correct. And if actually we're very unsure about that, then I feel like that the probabilities are going to come down quite a lot, actually. Now, they're probably just going to say, well, even if you deflate it by large factors, then the probabilities are just so enormous that the argument still holds. But then that comes to the question about how big are the probabilities. But before we get to that, I do want to talk about some examples here. I'm just trying to find actually the relevant section here. I think it was this. Ah, yes, here we go. So that there's a couple of other points, like about inflation and I think dark energy, that I wanted to come back to. But here is where he talks about some of the sort of standard examples that are given, like about the many of these relate to the masses of different particles here, and I can't even remember what alpha stands for here.
That's presumably that's fine structure.
Yeah, I don't know what the S stands for, but anyway, is this not quite large enough?
No,
anyway,
I just got it on a very small screen.
That's fine.
I think all your viewers can see it fine.
So a lot of these are masses and fine structure constant. I think there's a few others here as well. But that is not the main point I wanted to make here, is because it's not so much about which constants they are that's of interest to me. What's of interest to me is how is it established that how are particular parts of the parameter space ruled out as being non-life permitting? Because that's basically, now I want to scroll somewhere else. So just remember this page 42. I just want to show the idea of what he's doing here and of my critique and hear your thoughts. So this graph is for something specific here. And Luke presented one of these in the debate. This is what you typically see in the fine-tuning literature, right? This is what the mass of the down quark, and what's PL?
That's Planck mass. So
there you go. And so this is the up quark here. So these are basically ratios of masses, and these different lines here represent different constraints. It doesn't actually say in the caption what they are, but it doesn't really matter for our purposes. I'm just illustrating the point. Different constraints on what is judged to be parameter values that are consistent with a life-permitting universe. And there's this very small region here that satisfies all those constraints. So the basic idea here is you take a number of parameters, 2, 3, or however many, and then you plot some sort of representation of the range of values that they could have, generally in like logarithmic space here. And then you eliminate various different parts of that space based on particular criteria that you use to decide which regions would or would not be life permitting. So my interest here is primarily on trying to work out how is it determined whether a region in parameter space is life permitting or not. And this is the basis of my main criticism, which I outline in my book and I discuss with Luke. So looking through this list here, just as an illustration of sort of the point, we know that these different constraints on various parameters relate to the fact that for hydrogen to exist, for atoms to be stable, for chemical reactions to be of low energy scale than nuclear reactions, to have molecular structures, for it to have stable protons, to what is this one? Oh, well, this is stated differently. So to ensure that electrons are stable, basically, to ensure that carbon is stable, to ensure that electrical forces are stronger than gravitational forces at small range, at small components, and so forth. The point there is that all of the majority of these constraints are based on the need to have chemistry, essentially. Now, there are some other constraints, like the cosmological constant, which we'll get to later, but a lot of the constraints relate to the need to form bound states of like atoms and molecules and so forth. There are some others that also relate to star formation, but a lot of them are also sort of similarly constraints on chemistry and also nuclear reactions. So what I raised in the discussion with Luke is the problem of exotic life. Well, how do we know that somewhere out there in parameter space there are not large areas or points in parameter space, at least, which would allow very different types of life to exist? And my criticism is that these overwhelmingly, the fine-tuning literature seems to focus on seeing what combinations of parameters would allow basically chemistry, or even at the extreme case, maybe bound states of quarks and or electrons to exist. And I guess the question would be, why should we think that that's necessary for life to exist in some form? Obviously, it's needed for our life to exist. But what about any type of intelligent life? So what are your thoughts on this, Matt?
I generally, there's so much literature on it, and it goes into so many complicated things that it's hard to tell just how fair these criteria are. But from what I've read and from this paper, a lot of these conditions seem to be fair. Like, you're absolutely right that don't really have an idea of what you need for life. We don't really know what the necessary and sufficient conditions are for life to form. But based on the physics we know, we can make fair guesses as to for what values of these parameters things change so much that we're not going to get complex structures at all, let alone life, but any complex structures whatsoever. What I actually find quite interesting, though, from your argument, is that you say that there could be some large other regions in the parameter space which allow exotic forms of life. Well, that may be the case, but that seems to me to create more of a problem, because if there are these massive swathes of parameter space which allow for exotic life, then the argument then becomes, well, why are we this particular form of life when it seems overwhelmingly more probable that we would have been some other more exotic form of life?
That's interesting. I've not heard anyone raise that objection before, and I think the issue is that, well, I guess it depends what you want the fine-tuning argument to do for you. Of course, you can say, why with this form of life and not some other form of life? But that seems to be getting to something like the asking, like, well, why did this person win the lottery? Given that it would be extremely unlikely that this person would win the lottery. If you've only selected the person after they've won, then you're not establishing what the criteria was prior to observing the results. So whatever form of life we ended up being, supposing there were many different types we could have been, we could say, well, why are we this form? But unless there's some prior reason for saying, like, for asking that, you could just ask that regardless of whatever type of life we were, just as you could ask, well, why did this person win the lottery, irrespective of who won the lottery?
I mean, that's true, and obviously we're going to be biased because we are carbon-based life, and everyone who we're ever going to meet is carbon-based life, because once you're here, this is the only place we can really survive. But
well, this is the way the universe is, yes.
But if you do, this is why Boltzmann brains are a problem for cosmology, because what you need.
Do you want to explain what those are?
Oh, sure. So a big problem with various models of multiverses is that it's overwhelming. You get overwhelmingly more isolated brains spontaneously fluctuating into existence with all of your particular memories and then disappearing out of existence than you do proper observers in life like us that persists for certain region of time and find ourselves in a fairly low entropy region of the universe. So what multiverse theories have to be careful of is not overproducing Boltzmann brains. We want, the whole point, to avoid fine-tuning, really, we want to make sure that the average form of observer, the average form of life in the universe is our own. If you start producing infinitely more Boltzmann brains than ordinary observers, then it's overwhelmingly more probable that you should be a Boltzmann brain and not intelligent life sitting on a rocky planet in a low entropy corner of the universe. So that and that's what I think is the problem with saying that there might be some big other regions of parameter space that allow for exotic forms of life unlike us. Because if these regions exist, then it's kind of like the Boltzmann brain. The probability of there being of you being an exotic observer becomes so much larger than you being a carbon-based observer that we're no longer the mediocre average kind of life that you'd expect. You'd expect these exotic forms of life in general. If you see what I mean.
Yeah, I can see. So I sort of present this. I've heard this objection presented in a slightly different form, but the way I talk about this in my book is to hypothesize, and this is just a hypothesis, but I think it needs to be taken. Well, I guess I'm biased here. I think it should be taken seriously for people who are making this argument. Is that the structure of life-permitting universes may be in parameter space, may be kind of like I guess fractal in a loose sense, or highly complex. So in any given region of life-permitting, any given life-permitting combination of parameters might be sort of locally unstable in the sense that if we change the parameters a little bit, then that form of life wouldn't be possible anymore, just like ours appears to be. But there could be many different types of life, of exotic forms of life, such that the overall volume, or I guess hypervolume or whatever, of parameter space is quite large, even though locally, if you change the parameters a little bit, that type of life wouldn't be possible. So that's a form of local fine-tuning. It's like, well, yeah, things need to be particularly mixed up such that you can get a particular form of life. But it's just that there are lots of ways you can do that in the overall quite high-dimensional parameter space of all of the different parameters. Now, when I put that forward, a lot of people just think, well, you just sort of say, well, maybe, but I don't think so. But I mean,
it's a nice idea, and yeah, it's a nice idea. I can't see anything. There's not so much to rule it out, in principle. But
there's nothing to confirm it or deny it in principle. That's not the point.
But I feel looking at the kind of graphs that are presented in the papers that Barnes is talking about, it doesn't look like this region has this structure. Obviously,
yes.
If it did have this fractal structure, it would be incredibly difficult in these studies that are being done to see that, because what you're essentially ending up with is really specific areas that are life permitting, whereas huge or there are a lot of swathes of what they're doing in these studies are just looking at general swathes, general properties of each region, and asking when do those life permitting criteria fail. They're not looking for like microstructure, and that's basically impossible to do when we have no idea what life could be like. But these kind of diagrams where you do just get things where things are just too dense or things are too diffuse, that does seem to rule out swathes of a parameter space such that there can't be any fractal structure in that region. There's a point at which you think there's probably just no kind of life possible in these regions.
Yeah, right, and that's effectively what Luke said. And this is what I wanted to explore with you a bit more, because you know a lot about stuff, and you're maybe a bit more willing to discuss it than Luke was. I found he was a bit hostile at some points, but anyway. So, and he phrased it in the way that, what is it? The fundamental equations are linear in the parameters, basically, so that you're not going to get this fractal structure. But I feel that was sort of missing the point. and what you were saying in terms of the structure of the diagrams, we just showed some examples here that they do tend to look like this, right? They don't show the structure I'm talking about. But this is sort of my criticism. My criticism is that for most of these cases, maybe the main one that I think is a bit different is the cosmological constant. So if we put that to the side, most of these others are looking at questions of like, are stars stable, or when are atoms stable, or when can we have chemistry, things like this. And I'm not convinced that those are particularly relevant to establishing when complex life can exist. Obviously, it's relevant to our form of life, but we don't know what other types of life are possible. And I feel like physicists who are engaging this, well, it depends what claim they're making, right? But if they're making a claim about all types of complex life, I think that there's an immense lack of imagination there, because we've got the whole standard model to work with, and the life that we know only uses a few particles in that in a very particular energy configuration. And like, what can we possibly know about what other configurations are possible? And what they're looking at in these diagrams is just the types of life that we know. Like, we're assuming that, well, look, we need chemistry to have life. But I say, how do you know we need chemistry to have life? Like, why couldn't it be something completely alien to us? And the best argument, it just seems to me, and feel free to push back, it seems to me is just, well, like, we have no reason to think that such a thing is possible. But to me, that's question begging. If someone's going to make the fine tuning argument, I think they need to show that such things are at least quite unlikely, because they're saying that they know. This is what I argue in the book. The fine tuning proponent seems to be saying that they know what the structure of parameter space is like with respect to what is life permitting. I'm actually not claiming to know that. I'm just trying to illustrate the point that I don't think they know that. So what do you think? Feel free to push back here.
It's a totally valid point, because it's difficult to see the it's difficult to produce any consequences from any theory, really. I mean, it's so difficult even to derive the macro properties of a lump of steel by trying to derive it from. I mean, what they're trying to do here is they're deriving properties from some of the fundamental constituents, not even atoms, going even deeper than that. When in physics, it's hard to, as I say, to work out how a lump of metal is going to behave by starting out from the atoms. So in that sense, it's very true that varying these parameters and working out what happens at the micro scale it's very difficult to tell how this translates then to the macro scale, and whether you can get complex structures and whether you can get complex life. What I would say, though, is that I think that the things that are considered here, while they do sometimes consider star formation and things like that, in these particular diagrams, what they're talking about is really how complex how complex matter can be get to behave, and how complex the structures you can make this matter, you can get this matter to form. And all these kind of excluded regions seem to me to be plausible, fair regions where you could quite convincingly say that there are no interesting interactions anymore between the fundamental particles. There isn't anything to form structure. And stars come into that a bit. You don't want to rely on stars too much for precisely the reasons you're saying, because maybe stars aren't needed. But you do need something. If you've only got the reason there aren't huge amounts of the heavy elements in the universe is because without stars you just get the very basics. And so to get complex structure and to get complex life, you need something that's going to generate whatever you need to get this complex structure. And stars are like a stepping point. They're complex in a way, but sufficiently simple that they form and then allow the formation of more complex things like us. If you don't have any stepping stones, so that you can get increasingly more complex structures, then it seems to me that it's fair enough to rule out these regions of the parameter space, because does life exist in them? Perhaps, but either they lie on a fractal, and this fractal could be so thin that still the parameter space, there are far more places where life doesn't exist than where it does. but also I think it's what they've ruled out seems to me to be fair enough, that there's no complex structure, let alone intelligent life.
Yeah, well, let's talk about this notion of complex structure. So again, it seems to be that often what's meant here is some form of chemistry, or even, well, yeah, let's say elements other than hydrogen, or maybe not even hydrogen in some cases, depending on exactly what's been fine-tuned. But what I press is that I don't know why we're even looking at that, because why do we think that life needs any sort of chemistry? You're right, it obviously needs some sort of interactions between particles or fields or whatever. But there's a lot of space for that in the four forces. I mean, I talk about, look, life as we know it uses, well, I guess the strong / electromagnetic force, depending on the scale you're talking about. Mostly electromagnetic at the beyond individual atoms. And then, but then there's the weak force, and then there's gravitational force as well. Plus, there's other instantiations of the like other types of hadrons, for example, that we don't even really know much about, or are only very unstable in our universe. Plus there's 3 generations of matter, and pretty much everything we know about is only 1 generation. Plus we've got dark matter, who knows what that is. Plus we've got dark energy, who knows what that is. And like these are just some things that I know about. Like I'm no expert here, and probably there's other possibilities. Like I don't know anyone who's even trying to think about what sort of complex interactions could hypothetically exist in n-dimensional parameter space in the standard model.
I guess one of the things is that we do, in a way, have an example of physics where life doesn't form, because we can look at all these things that you're mentioning. We can look at strange quarks, charm quarks, top bottom quarks, and we see that there aren't people made out of strange quarks and strange chemistry. It as far as we know, it looks like these things don't form complex structures and don't form life. They decay too quickly. And
yeah, but that's in our universe.
True, but if you want to view these other families of quarks as being the up and down quarks, but with their parameters change slightly, their masses are slightly different, and things like that. Because you can't change the fundamental constants, but you can. If you're looking at ratios of masses, you can see that the strange and charm quarks are just the normal quarks we have, but their masses are slightly different. So in a way, that's as close as we can get to trying to work out experimentally what the effect of changing parameters has on the ability to form life. And strange and charm quarks just decay. They just when with the masses that they have, they just decay, and it doesn't seem. It seems pretty plausible to me to say, when things like this happen, when all the particles that you have immediately decay, or when the particles you have don't seem to form bound states, then that seems to me to suggest that it's pretty plausible that these regions of parameter space won't support life in any form.
Well, this is similar to what Luke said. So I mentioned the weak force, and he said, but there are no bound weak states. But I mean, I said, well, yeah, not in our universe. But the question is, are there regions of parameter space of their own? And as far as I know, that's an open question. So, and again, I don't think there are too many people looking into these sorts of questions. I did a quick search, and it looks like there's been a couple of people who looked into that. But so I'm not an expert there. But the point is, I'm just not persuaded by saying, well, look, we don't have weak bound states in our universe. Charm and strange and other quarks are unstable in our universe, and all of these other things. When we're not talking about our universe. Precisely the point is asking what would happen if the constants were different, especially I'm thinking about many of them being different, maybe not just a couple, but I'm talking about the structure of the overall parameter space. And I guess, maybe at the end of the day, it's just a clash of intuitions, but my intuition is that space could look like who knows what. As far as I know, the space probably looks like what the small region we know, which is that we know that our region of parameter space supports life because, well, we're here. And we know that if we modify the parameters either way, we don't get our form of life. So why not think that that is what actually the whole parameter space looks like? Except obviously it's not going to be our form of life. It's going to be other, or at least complex structures, right? Maybe we'll just say complex structures. It seems, well, not unreasonable to me that that's what the whole thing looks like. It's just very different forms of complex structures. Whereas other people seem to just have the intuition, and I admit that this seems to be the overwhelming, well, I don't know about everyone, but at least the majority of intuitions that, well, we don't see any reason to think that there would be any complex structures here, and we don't know of any things that would form, so we're just going to say that probably there aren't any. I mean, what do you think about that? To me, it seems rather unsatisfactory that there's just sort of a clash of intuitions there, but maybe, you know, maybe there's more to say in favor of your view or my view that, well, you'd want to bring out there.
I mean, it seems, I can understand your intuition that it's unsatisfactory to say that when these conditions stop holding, there's no more life, when it's so difficult to in another universe where things are completely different, how do we know? But I think even if that argument holds, you could just focus on what do we need for our life? If you just focus on that smaller question, then these graphs are undeniable in the sense that these basically show that as soon as you change the parameters very slightly, life as it's formed here, just there's no chance of it forming whatsoever. And that there's such a small region of parameter space that supports our life is interesting on its own before you start thinking about, well, there could be other regions of parameter space, there could be other universes which support life that's very different to ours. But I think that I guess this is how my intuition goes. Looking at that there's such a small region of parameters that allows for life as we know it, that seems to be a significant enough conclusion. It didn't have to be that way, I don't think. It could have been that there was a much larger region of parameter space, but because there's such a small region, that leads me to thinking that, okay, even if there are lots of other ways you could have life, it feels that the regions that support these could well be just as small as ours. And then if they were much bigger, then this was the point I raised earlier. If they are much bigger than the region that we're in, then why aren't we that form of life? I can see why you stick with your argument, but for me, with my intuition, it worries me. It doesn't seem to me to be it seems too speculative it seems almost like a hope that there will be these other regions of parameter space which allow for life when to me it looks like the evidence suggests that it's quite small and perhaps always going to be quite small, which is why I rely on other arguments to do with probabilities, which we'll get into later. But
let me just ask about that speculative aspect, because that's something that I agree when you say that even if we just restrict ourselves to saying that our type of life is sort of locally fine-tuned in the way that I've explained, even if we just restrict ourselves to that itself is an interesting and important observation. I completely agree with that. And so I'm not intending to diminish or demean that result. I'm, of course, more interested in the use of this as an argument for theism. It's there where I want to push particularly far, or maybe not far, but push and ask, well, can we establish what has allegedly been established here? Now, I wanted to pick up something you said, which I think is super interesting there, because I think that this is exactly the response or intuition or whatever that a lot of people have, which is that when I say, well, what about all these exotic forms of life? They'll generally say, well, look, we can't show that that we can't prove that those don't exist, but they think it's very speculative and it's kind of like wishful thinking. Now, I guess I have the exact opposite intuition, and I just want to see what you think about this, because this is actually just really interesting to me from a disagreement point of view. My intuition is exactly that it's the person using this argument for theistic purposes, or I mean, I suppose for another purpose, but usually it's a theistic purpose. So again, I'm not talking about people who are just studying, let's say, local fine-tuning, but people who are saying that there's global fine-tuning and using that for a purpose. It seems to me that they are the ones who are speculating and maybe engaging in wishful thinking, because they claim to know, at least with reasonable probability, what the global structure of life-permitting space in parameter space looks like, whereas I claim not to know that. And I claim that they don't know it either. So even if I mention specific things like, bound weak states or other generations of matter, or whatever stuff I come up with, that's all speculative, obviously, but those are just attempted to illustrate the idea that we don't actually know whether any of these things are possible. And so, yeah, just as someone says, you're just speculating about an exotic form of life, I say you're just speculating that those things are not possible, but claiming that you know that. Do you see what I'm saying?
I see what you're saying.
Like,
what I'd say is
and
that,
feel free to disagree with that.
I guess I disagree that it's pure speculation. It's like you can know, at least you can draw a line and select a region of parameter space, and you can say, in this region, we know you get one type of atom, not even atom, you get one type of particle that basically doesn't interact. Do you think life can form there? I mean, we can't know, sure, but
oh well, no. If there's only one type of particle that doesn't interact with anything else, it's pretty unlikely to see how life could exist. But the question is, has that been established, right? And I'm not convinced that it ever is, because what I mean, there's always, you know, a paper that you know, well, what about this paper? But again, that's the reason I showed some examples there. But people aren't looking for what are the full set of interactions that could exist with this full set of parameters. And I mentioned this in my debate with Luke as well. They're looking at, okay, if there are these couple of parameters, can we get chemistry, or can we get stars, or can we get hydrogens or hydrogen atoms, or whatever it is that they're looking for? And then they'll maybe say, well, the whole universe is hydrogen, or the whole universe is you know, something else. And well, yeah, sure, then you're not going to have chemistry or whatever else. But my question is, what else is happening in the other parts of, or in the other parameters that you haven't even mentioned? Because you know, if I have a two-dimensional space and I just look at what happens on those two dimensions, I'm completely missing what's happening in the third dimension. So this is a point that I make in my book. The fact that there's multiple dimensions here, and I mentioned this in Luke Barnes' debate as well, that actually makes the problem really hard, because missing any one of those dimensions could miss most of the interesting thing that's happening. If you imagine that the structure of the space is highly complex in terms of what's life permitting, that some combinations of this force can give rise to life in this combination, but other combinations of a different force in another complex, and then so on and so forth. Like, our form of life requires the strong nuclear force to operate in a particular way to give rise to atoms. But then at a sort of larger scale, it's mostly electromagnetic that binds those together to form molecules, for example. And the weak force plays a relatively small role, although obviously it's radioactive decay and things, but it's not, you know, it's not responsible for binding stuff. And then gravity plays a role as well, but it's kind of just clumping things together. It's not responsible for microstructure, right? Now, so those are the four forces and the roles they play at a very crude level. Now, imagine just shuffling those around and saying, well, actually, the weak force does this and the strong force does that. And or then maybe you could have more of the forces playing a role, or fewer of them. And when you think of it that way, the whole picture could be extremely complicated in many different dimensions. And then the question is, and then as a result of that, the claim that, well, I've looked at a couple of the parameters and you only get hydrogen, to me just seems not really very informative.
I think what I'd say is that I take this kind of evidence and the fine tuning, and then think, and to me it then makes me think, let's be cautious about thinking that lots of the parameter space of the much higher dimensional parameter space could be lovely and life permitting. This doesn't lead. I think I agree with you so far as to say that all these considerations shouldn't lead to grand claims that that the only possibility for life is in this tiny region, and that this tiny region is all that could ever possibly allow the existence of life. But seeing the research that has been done, and because this research it's so complicated to say when something is life permitting, and you do have to make some compromises, and so you're looking at things like chemistry forming instead. The research that's been done, and that it looks to be the case that the region that's life permitting in phase space appears to be so small, to me that then means that while I think there's nothing wrong with your argument per se, it's not one that I'd personally be comfortable relying on.
Yeah, that's completely fair. I just one final thought on this. Then I want to talk a bit more about the dark energy, because I think that's a particularly interesting example. And then we'll move on to some of the other issues I highlighted at the start. So the final observation here is that I have a hypothesis for why I think about this in a different way to at least a lot of the other people I've interacted with, both atheists and Christians on this point. I don't have any evidence for this. It's just speculation, but I'll be interested to hear what you think about it. Then the hypothesis is this. Although I do have a physics background, but I'm not a physicist, and that's not my main area of research. I guess for me, it's I guess more of a biology/psychology kind of background. Basically, I think about things more as a biologist than as a physicist, although maybe I'm a bit in the middle sometimes. But and I think that's interesting because in biology, well, things are very messy, right? And it's sort of like, if you think about it this way, if you go to a random region of Earth and you ask could there be life here? And intuitively you're like, well, obviously in some regions, yes, but you go out in the desert, say, well, how could there be life here? It's just all sand. But then you dig into the soil and you find that there's all these species of bacteria, or that there's lizards that come out at night or whatever. Or you go down to a volcano at the bottom of the ocean and you say, well, there's no way there could be life here. But then you find that there are extremophiles that are living there and so forth. Now, obviously, this is just an analogy, right? I'm not saying that this is directly an argument but the point I'm making here is simply that I think the fact that things are so complicated and messy in biology, and you have so many different adaptations of life in many different contexts, and well, there's other things I could say, but just to illustrate that point, leads me to think in kind of that way. Whereas physicists just don't think about things, I think, in quite the same way, and they maybe think about things more in the way I'm showing here with these diagrams with the parameters in particular, cutting off things. So that's not really an argument for one side or other being right. That's just a hypothesis for maybe why the intuitions vary. So any reactions to that?
It's an interesting idea. I think I agree with it a lot, and I think what the way that I think about all these graphs is then, I guess that what we're looking at is not just looking around the Earth and looking at deserts and volcanoes and thinking, oh, life's probably not there, and then finding it there. What I feel physicists are more doing is then leaving the surface of the Earth and looking at empty space, looking at things like empty space and asking, life can't possibly be there, and the evidence seems to back that up. And that's what I think is happening in these graphs. We're looking at really massive swathes of the parameter space of our parameter universe, and we're saying that these regions are basically like empty space versus Earth, where in the small region that's life emitting, this is like Earth, and there's maybe some extremities of it that you think could life form here, maybe not, but maybe then you go and find that it does. But then we're also looking at a wider swathe of this parameter space, and we're saying this stuff is basically like the equivalent of in your analogy of the depths of space. We're pretty sure that nothing's going to turn up there. We could be wrong, but I guess that's how I see it. But all this biological and definition of life stuff is messy, but sometimes it looks like the areas of the parameter space, they just don't allow for anything even conceivable to happen, and so it's safe enough to rule them out as saying there's nothing interesting going on.
I guess my point about mentioning that is again, it's not an argument. It's more just to explain where the intuition of conceivability comes from. And I'm just fundamentally unconvinced by why we should think that these are inconceivable. But of course, I can't give an argument for that they are. And my main call is for more work to be put into actually trying to think about other ways that complex structure could arise, rather than just ruling out. Because the way it seems to be is entirely negative. It's how can we put bounds on where we can get the current set of complex structures, as opposed to let's see if we can build toy models as to what other combinations you could have bound states or other types of interactions. I guess that would also be interesting.
I guess there's one example of where that has been done, which is Conway's Game of Life.
Oh yes, right. That's a good example. Yes,
but I find that whereas this is a really simple system that does generate complexity and complex structures, and perhaps you'd call them life, maybe, but at the very least, this is a really simple system that almost unexpectedly gives you a really complex array of structures. But I feel that kind of supports my the development of Conway's Game of Life supports my point more, that there were lots of other rules that they tried to do and found nothing. And it seems then that both in the physics of the world we're looking at and also in the cellular automaton world, there's only a very small set of parameters that generate complex structures.
Yeah, Luke mentions that in this paper as well. I also cite that example in my book, although for a slightly different application. But yeah, I saw that was really interesting. And hopefully the viewers also found that discussion. I wish I could have pushed Luke. We could have had that exchange a bit more with Luke, but he, again, was a bit grumpy when, when I asked him how he knows that life's fine-tuned. But anyway, I want to move now to talk about, well, it's kind of another example of what we're talking about, but I think it's sufficiently different to warrant a bit of its own discussion before we move to the probability space arguments, and that is the cosmological constant. So this is really quite different because it's not, the cosmological constant is not it's not part of the standard model of like particle physics. It's a cosmological well, it's constant obviously, but it's a cosmological constraint, I guess, on the evolution of the universe. So the basic idea here is that the cosmological constant is something that appears that it needs to be fine-tuned, because if it's too high, the universe will rip itself apart too quickly and we won't get life. But if it's too small, then the universe could recollapse on itself and too quickly for us to get life. So the idea there is it appears to be fine-tuned to have to allow a universe to be sort of reach the old age necessary for complex life to emerge. And so I don't definitely Luke in his book talks a bit more about this. The discussion here I found a bit sort of hard to follow. But anyway, I'd be interested what you think about this particular example of fine-tuning, and just what your thoughts are about it.
So I think this is one of the few areas where I think I agreed on the whole with what Stenger had to say.
What does Stenger say about this?
It's basically that
one?
Yeah, the reason that this cosmological constant problem is a problem is because you try and calculate it from quantum field theory considerations and you get a number which is just totally ridiculous. It's so wrong that I kind of agree with Stenger that it just, in a way, just shouldn't be taken seriously. And I found Barnes's comments on this interesting, but I think ultimately unconvincing. So the fact of the matter is, if you do try and calculate the contribution to the vacuum energy from the matter fields that we know of using quantum field theory, you end up with this ridiculous parameter, with this ridiculous value that isn't the case at all.
Just explain why it's ridiculous. I think you sort of did, but just clarify for people who aren't familiar.
It's simply just ridiculous because you can see there, it's 10 to the 120 times greater than the observed value.
Yeah.
So, is this the worst agreement between?
That's what I was told.
I think it is. I certainly haven't come across one that's worse than this. I mean, this is such a massive discrepancy. It's almost inconceivable. And I agree with Stenger on the surface that this calculation has gone so wrong is probably more an indictment of using quantum field theory to calculate this than a suggestion that we've got a fine-tuning problem, is what I feel. What Barnes has to say about this is that even if we develop more fundamental theories of physics and there's a more correct framework for doing this calculation, I think he seems to say something along the lines of it would still be true that the matter fields that we do know of would still contribute this massive quantity, and that in order to get the tiny value we observe, there's got to be some massive fine-tuning between all the contributions we don't know that brings it down to some there's got to be some miraculous cancellation between contributions we do know and contributions we don't know that ends up in a value that's very, very different. I don't know a huge amount about how this calculation might change. I'm not sure that anyone does really, because it seems to me to be something that's going to depend on details of a quantum theory of gravity, because the cosmological constant is something that appears in Einstein's equations. It's something
well,
that
he put it in there because he didn't like the idea that the universe was expanding.
he originally put it in, took it out, didn't like it, and now it's back in. But it's in our theory of general relativity. That's where this constant appears, and everyone knows that general relativity and quantum theory don't get on too well. And so for me, it feels like trying to calculate this value using quantum field theory, the fact that it's gone so wrong suggests to me that, well, this is just a really clear example of that we shouldn't use quantum field theory to calculate things that that are gravitational in nature. I think Barnes disagrees with this. I think disagrees with this line of reasoning.
Yeah, that's what he was saying here.
He says something along the lines of that. Even if there's a quantum theory of gravity that does get the right value of lambda, that this is still a massive fine tuning. This is still a fine tuning problem in how it's cancelled out the 10 to the 120 times larger contribution we get from the matter fields that we do know. But to me, this cosmological constant problem feels like something we've glimpsed a problem that is only going to be solved by theories of physics that we don't know yet. And so speculating about what this problem means for fine tuning and for us at the moment seems to me to be premature and even uninteresting. Even though the cosmological problem itself is fascinating, we've got to find a reason why our calculations have gone so wrong, and I'm sure the reason why they have is fascinating. Yeah. But I feel that it's something that is just beyond our current level of explanation and beyond our physical theories at the moment, and that speculating on it too much, and that it's generally just speculation at the moment.
Yeah, this is pretty much what I said with respect to when this came up in the debate I did with Luke. I think I commented, I can't remember what I said in my book about it, but because dark energy and the cosmological constant is one of the least understood aspects of current physics. I mean, it was only discovered in the 90s, I think, the accelerating expansion of the universe. Yeah. So, we clearly have no idea what causes it. So I think making much of any claim on the basis of that is pretty premature, although it is certainly super interesting. But I wonder, actually, this would be interesting to get your thoughts on it. I've got to be careful how I phrase this. So obviously we don't currently know what the cause of dark energy is or why the cosmological constant has the value that it appears to. And so figuring that out is going to require extension of our physics. But do you think, or is it generally thought that, be careful how I phrase this, do you think / is it generally thought that explaining dark energy will require new physics, as in like extensions to the standard model? Or is it more like probably it's to do with the way we're performing the calculation in the context of quantum field theory / maybe gravitational effects coming into it, and not so much like that there's stuff outside the standard model?
I think it's something that I think the solution to this will have to come from beyond the standard model physics. Because the cosmological constant is something that appears in general relativity, we do have a very limited theory of quantum field theory that does mix with gravity a bit. You can do quantum field theory in curved space, and what the reason this works is because you assume that all your matter fields are very weakly coupled to gravity. So gravity doesn't play a huge part, but a small part, and you can get sensible answers and sensible physics out of this thing. To me, what the cosmological constant is it's the vacuum energy, and this feels like something that's got to calculate this properly is going to require a knowledge of everything that contributes to the vacuum. And so if your knowledge of what all the matter content and all the matter content that's also related to to gravity, if your knowledge of that is limited, then you're always going to end up with the wrong value for the cosmological constant, because there'll be other things that are contributing that you don't know about, and their contribution could be completely different to the ones that you're looking at. The contribution for the matter fields that we do know of is so ridiculously large to me that just suggests that, well, there's probably some there's some matter fields we don't know about, or there's some way in which gravity and quantum theory combine that we have no idea about, and this is what's going to solve the problem. I don't think there have been many suggestions, to my knowledge. I don't think there have been many suggestions of how to solve the dark energy problem with matter fields we know about. I think they almost always introduce new fields, or they take the cosmological constant to be the vacuum energy, which is going to get contributions from every kind of matter that exists, and we certainly don't know what all those kinds of matter are.
Yeah, well, that's actually interesting from my point of view, because the more new, the more new physics comes along, the more possibilities there might be for exotic forms of life, right? Even if those are not, like, this is actually something that I've thought about. There may be a lot of physics that is so, I guess, weakly coupled to anything that happens in our universe that we just don't know about it. Like neutrinos would be an example, but we've only known about those relatively recently. These are very small, small particles that are very weakly interacting, and they build like these big, not even swimming pools, it's more like mines that they fill up with like water or
massive fish
detergent
tanks,
or something, to detect just a few interactions because it's so weakly interacting. So I wonder whether there might be more stuff that's going on like that. Obviously that's speculative, but I just think it's interesting.
You do wonder things like, I think neutrinos are probably the least understood matter that we have come across. And what's fascinating about neutrinos at the moment is that they're one of the few cases where we 100% know that the standard model is wrong, because you can't get the standard model entails that neutrinos are massless. They have zero mass. But we know now, and also that they conserve flavor. If you have a kind of neutrino, it stays the same kind of neutrino in the standard model. But we know two things that contradict that. We know neutrinos have a small mass, and we know that they change flavor as they travel. So there's two effects there with neutrinos that we know completely contradict the standard model, and so they're tantalizing hints as to what could lie beyond it.
Yeah, very interesting stuff. And partly this is why I get annoyed at people who take this and try to use it for theological purposes, because I think that it's interesting enough in itself, and we should take it for what it is. But anyway, let's now move. So we've been talking a lot about how we can establish fine-tuning, and we talked about, I guess, if we're sort of looking at this contents page here again, we're using this as the basis for our discussion, not necessarily following it super closely. But we've talked a bit about like the laws of nature and star formation and the different masses of particles and other forces. We also just talked a bit there about the cosmological constant. There's a few other points here, but I don't particularly want to get into those right now. I want to talk about your concern, Matt, about moving from parameter space, which is the different combinations of possible parameters that you can have in the standard model and cosmology, to a probability on how likely it is that we would see different regions of that space. And so the typical, as you pointed out, Luke doesn't really say much about that in this paper. Other people who advocate for the fine-tuning argument do, and they give various arguments for why but basically what they want to do is they want to use something like what's what I'm looking for, a uniform distribution over parameter space, which means that you have extremely wide ranges of possibilities, which all have basically the same prior probability, and then the actual basically a small space in parameter space corresponds to a very small probability, and that's how you get very tiny probabilities in the fine-tuning argument. So you're quite, maybe I'll stop this for the moment because it's not directly relevant to what we're talking about. You're quite skeptical about that. So what are your thoughts on this?
So let's start with just the uniform. What are the arguments for it being uniform? Well, the arguments for it being uniform essentially rely on epistemic considerations. Yeah. as far as we know, it's consistent. It's consistent with the laws of physics that we know, just to vary these parameters and see what happens. And in that sense, there's no reason to think that any value of the parameters is more probable than any others. And so that's kind of the argument that proponents of the fine-tuning argument use to say, well, then small area corresponds to small probability, and so there's a small probability that life should exist if we picked a random universe. But I mean, I feel you could make the total opposite argument based on epistemic considerations as well, because you could just say, well, this is the only universe we're in. As far as we know, these are the values they take and they can't change. So then your probability is 1 in the region we've measured it, and then 0 for all this other.
Because we measured it and we know it's not the other ones.
Exactly.
Basically.
So you can say, well, based on what we know, it's this value, and so the probability that there's a life-emitting universe is certain. So this kind of epistemic justification seems to me to be totally meaningless. You could argue for any probability distribution you want based on what we know about what values these parameters could take. And the reason for that is because we have absolutely no idea what the values these parameters could take. So what's more interesting is to think about where is physics going, and what does that mean for the possible values these parameters could take. One way it could go is that these parameters, a lot of the parameters we see at the moment, a lot of the constants, they could be fully determined, and that there was no probability of them being any other way, because their values as we see them are determined by higher energy theories. What we see is just a low energy theory, and certain values in that low energy theory cannot be predicted from the theory we know about currently. To get their values, you'd have to know what the higher energy theories are and what they predict. And so it could be the case that a lot of the constants we see are just
I'll keep going. I just
found it quite interesting. So yeah, it could just be that the constants that we see are generated dynamically by the higher theories, and they couldn't have been any other way. But you could take that line of thought further and think, well, is the goal of physics to end up with a theory that there are no free parameters and nothing could have been any other way? And then that seems unlikely. It could be the case, but it also seems unlikely, and you wouldn't want to place your bet on that too much, because as I said earlier, I mean, there are lots of consistent mathematical systems out there. A square, a triangle, they're self-consistent. The real numbers are all self-consistent. So just having a mathematical physical framework with no free parameters that's self-consistent, you then ask yourself, well, why that mathematical framework over another one? And that gets into some very interesting considerations of what reality could ultimately be. But yeah, so one thing that could happen to these parameters is that we find out that they're determined by something, that they're fully determined by a higher energy theory. The other way it could go, it could be that these parameters can take a selection of values, and if ultimately you end up with parameters that can vary, perhaps they vary because they can take other values in other regions of space, or other regions of other disconnected space-time regions to our own. A multiverse kind of picture. There are so many different multiverse pictures, but for now, let's just ignore that. You could have a multiverse picture in which, in all your different pockets and all your different universes, there are certain parameters that vary between universes. And so that's the other way it could go. Perhaps there are more ways, but those, to me, are the two clear directions. And some of these constants will almost certainly be determined by higher energy theories and won't have any freedom. That's probably the case. But then some of them may be fundamentally variable. and not actually constant in a fundamental sense.
Well, yeah, so some of that seems to be leaning in the direction of multiverse theories, depending on how you interpret that. So, but putting that to the side for the moment, because we'll get to that in a little bit. But focusing on this question of how we apply a probability distribution over a parameter space. So what you're saying is effectively that, I mean, you can make whatever argument you like about that, depending on what information you condition on. If you just say, look, given the equations that we have, what could the parameters be? It's basically, well, it could be anything up to when the theory breaks down, which is what the fine-tuning proponents usually talk about. Yeah. On the other hand, if you condition on experimental evidence as well, it's a very small range of experimental error as to what they could be. Now, but the way that the argument is usually formulated, and I think Barnes specifically says this in his paper, is that he's formulating it as a counterfactual argument. And this means that he doesn't actually have to say that the constants are different in some other multiverse, or I mean, he wouldn't want to say that anyway, or like somewhere else in the universe or whatever. It's just that in another possible world, the equations of the laws of nature are the same, but there's a different constant, or the constants are a bit different. And so that's a counterfactual formulation. Now, that's a claim about metaphysical possibility, that there's a not a physically possible, but a metaphysically possible world in which the constant has a different value.
It is, and then it is though also a claim about physical possibility, because the values that a certain parameter could take, a certain parameter in our low energy theory could take, depend on what the higher energy theory is. And so it could be the case that some of the in all these graphs that we've shown, some of the regions in them just aren't. They couldn't even, in principle, be generated by a higher energy theory, by a consistent higher energy theory. This is actually a very current topic of research, especially in string theory, but also it's branching out to a lot more areas as well. What we're very aware of in physics is that we work with low energy theories that must come from some higher theory, and we can speculate as to what key properties this higher theory has. And what's been discovered and what's being researched at the moment is that there are only certain values of parameters in your low energy theory that could consistently come from a high energy theory. So what this would mean for the fine-tuning stuff we're discussing at the moment is that some of the regions on the parameter space could be just ruled out entirely,
right? Because
they can't come from any sensible high energy level physics. There's no way that they could have ever taken those values.
Well, because we don't have a full theory of what high energy physics looks like, we don't really know, other than there's probably constraints there.
Yeah.
Let's suppose though we had a completed physics, right? And let's suppose that in that completed physics, there's at least one free parameter. Again, we don't know that, although I think there probably will be, but let's just say that there is for the sake of argument. Then we can run the argument then, and then we don't have to talk about higher energy physics, because we've got the full final theory of physics, assuming there even is such a thing. But again, just to see where this goes, right? So then we could still ask the question: what can we say? So we're assuming we've got the completed theory of physics, but we haven't got completed philosophy. I guess if we had that too, then we'd kind of be done. But so we could still potentially ask the question: what we could ask about what possible worlds. Well, we could talk about possible worlds. I don't want to imply that possible worlds exist, so I've got to be careful there. But in different possible worlds, the parameters, the free parameters that do exist in this final theory are different things. And then we could ask, why is it that we find ourselves in the actual world instead of these different possible worlds that have the different constants? And if it is the case that only this the actual world, or a very small number of possible worlds around it, give rise to or allow for the existence of complex life, then it seems you've got a fine-tuning argument, or you're on the way to making a fine-tuning argument. If you can make the argument that the probability distribution that you've given over other possible worlds is such that the life-permitting ones are very implausible. So what do you think about that aspect of applying the probability
I think
over possible worlds there?
When you get to such a high stage as that, if you have your final theory of physics and you're talking about possible worlds, then talking about probability distribution seems bizarre. What does it mean? when you say that there's a
Yeah.
10% chance that that we're in a life permitting universe, what does that probability mean? I mean, it can't be frequentist. If there's only one universe that exists, then there's no frequency of it. You're not comparing how many life permitting universes occurred compared to how many non-life permitting universes occurred. So what does that probability actually mean, and where does it come from? What determined that the actualization of this set of universes was 10%, and the actualization of this other set of universes was the 90%? What would determine that? What would and what would it mean? So
yeah,
when we get to that level, probability to me seems and putting probability distributions seems, I have no idea what would ever determine that. What you could know, what fact you could know that would tell you what the probability distribution over these possible worlds would be.
Well, yeah. So I'm not sure. I'm just going to be devil's advocate and see how far we can go with this, because I think this is very interesting, right? So you're right. It can't be frequentist because, well, there's one universe outside of multiverse models, but we're putting that to the side for the moment. So probably it's some sort of Bayesian probability, which relates to basically subjective credences that people give to different outcomes, or different possibilities. So how could I, if I wanted to explain what the probability might mean, how might I describe it? Well, here's just the thought. So maybe the probability given to a certain subset of possible universes would be something like the credence that a hypothetical observer would give who knew what the laws of physics would be, but didn't yet know what the constants were. Like, they knew what the completed laws of physics were, but there's some sort of veil of ignorance or whatever, and they don't know what the constants are. So the question is, what subjective credences would they have about how likely the different, well, I probably shouldn't use the word likely there. What are the subjective credences they would place on the different possibilities? And the argument would be that they would use some sort of principle of indifference to say that, all of the possibilities are equally likely as far as they can tell. So they're just going to use a uniform prior over the possible parameter space, again using a completed physics, because we're assuming that they have that. Now let me just finish this thought, because maybe you don't like that. Maybe you say, well, that doesn't make sense for this or that reason. I think you could probably construct an account something like that. But what I would probably, I mean, again, you might object in a different way, but the initial thought I have is, okay, so you can construct that account of what that probability means, but why is that even interesting? Like,
yeah,
why? So yeah, is that you can go ahead then.
Yeah, that was going to basically be my objection, is that if it's a subjective credence
in a specific circumstance, right? That I've outlined.
Yeah, sure, in a specific circumstance. But even if it's a subjective credence, why do we care? What we care about is why this world was actual, and that reason should be independent of what we believe the law should look like, and what and all this kind of stuff. So what we're interested in is what if there is only one particular world that's actualized, why it was that one, and the probability distribution, the objective probability distribution, whether there was some cosmic coin that got flipped, or cosmic dice that got flipped, and there were 6 possible values for this constant, and it was a fair dice. Maybe it wasn't a fair dice. I mean,
yeah,
the credences are fine. You could perhaps come up with credences based on your situation and that kind of thing, but that's not what we care about. What we care about in these fine-tuning arguments is why this particular universe would exist rather than not, and why this particular universe maybe was more probable or less probable to exist than not. I don't particularly care what people think the likelihoods are.
Yeah, well, partly that's going to depend on how your philosophy of probability and when you think it's appropriate to deploy certain concepts. I don't really want to get into that now, but I think that is relevant here. As someone points out, Barnes does use, I know, Bayesian principles in his defense of fine-tuning. I can't remember how much. I don't think Robin Collins uses it as much. But anyway, I think that I'm not as familiar with that aspect of the argument, because I focus more on can we establish as fine-tuning? And also the second part is it like, well, is God a good explanation, basically? Yeah. But anyway, the thing that I think is interesting there is I think you can give accounts as to what the probabilities might look like. Because again, the reason this is important, just to sort of step back a bit here, is that in order for the fine-tuning argument to go ahead, you need to basically say what we actually see is very unlikely under naturalism, basically, or under a single universe naturalism.
That's what they want.
Yeah, and theism renders it more likely, so we should prefer theism. That's the essential argument. So then we have to say, well, how do we know it's unlikely? And there's usually a two-step process there. It's first of all saying that complex life is a very small regions of parameter space that allow complex life are very small in parameter space. That's the first part of the discussion we talked about. And I'm skeptical of that. Matt thinks that's a bit more justified. But irrespective of that, then there's the question of how do we put a probability distribution of how likely these regions of parameter space are? And that's what we're talking about now. So if you're going to put a probability distribution over that, you've got to defend like where you're getting that from. And that's not an entirely trivial thing to do, as we're pointing out here. So I just gave an example of how I thought you could maybe defend that as a credences that a hypothetical agent who knew the completed laws of physics but didn't know the parameters would have. That seems to make sense to me. The question then I would raise, and we were just talking about, is why should we now conform our beliefs to that hypothetical agent? Because we're not in that situation. That's a completely different situation to what we're in. So what relevance does it have? Like, you can use it to say that, like, to explain how you would get a uniform prior, but it's just not clear to me, and Matt as well evidently shares this view, that why that's particularly relevant to us. Because you could just as easily say, well, look, we've measured the parameters and we know more or less what they are. So that's what we should believe that they are. And it's not clear what other basis you would have for assigning probabilities over hypothetical other possible worlds.
Well, it's like in quantum mechanics, the probabilities for what your measurement outcome will be are determined by the physics, not by your credences or things like that. There's a matter of fact as to how these probabilities evolve, and then when you come to do your measurement, there's a well-defined objective set of probabilities that determines the probability of seeing each possible measurement. And if we're talking about a probability distribution over the values of constants, it's that kind of objective distribution that matters. It's one that actually objectively determines what the probability is that one of these universes would have become actual. And if there's only one universe and this objective probability was such that that a life permitting one was very, very, very unlikely, then fine-tuning gains some traction. But on the other hand, if we get to this ridiculously high level of physics, perhaps it becomes very clear that the probabilities favoured a life-permitting universe. What I want when we're talking about probability distributions is I want to get to that objective level where you get an objective probability for each possible universe becoming actualized.
So one more avenue on this point, I think what the fine-tuning proponent is trying to get at with the probabilities, and by the way, I do think you can run a fine-tuning argument without using probability language, because that does avoid some of the problems, although it's less precise then. But what they're trying to get at is, I think, the question as to why this universe and not some other possible universe that, as far as we know, could have been. Obviously, if we have a completed physics, then maybe that rules out some of the universes that we thought could have been, but turns out it doesn't actually work. But still, if there are some free parameters, there's going to be other universes that, as far as you know, could have been. That's the counterfactual there. It's not actually, but it could have been. Just like if we see that someone wins the lottery, we might ask, well, why did they win the lottery, not someone else? And there is a story you could give there, I guess, if you knew enough about the precise, positions and velocities of the balls in the machine or whatever it is, however they generate it, I suppose. You could potentially have an answer there, although it's not really going to be a very informative one. But then the question is, what sort of answer could we give as to why do we see this universe, which it seems unlikely that we would see it because it's life permitting, and most of the ones that it seems we could have had aren't. Now, in that formulation, I haven't really used probability language, at least not directly. So what do you think about that kind of way of formulating the argument, or at least a question, I suppose?
Right. So I think what matters, even though they can formulate it in that way, if it was more probable that a life permitting universe existed, then the argument, you can ask it and it kind of makes sense, but ultimately you don't need a further explanation for why there's life in the universe, because that was the most probable outcome.
Well, hang on, but how do we know it's the most probable outcome?
So sorry. So what I thought you were doing was you're posing the fine tuning argument, but in a way that asks, why are we this universe opposed to another? Yeah.
That, as far as we know, could have been. Yeah.
Yeah, that as far as we know could have been. Well, that is a legitimate question. So I guess there's two routes you could go down. Let's suppose that there is actually an objective probability for a life-emitting universe to exist. If it's very probable, then the question this person's asking, why are we a probable universe over an improbable one? It's still a question you can ask, but I guess it's still an interesting question, but it doesn't establish that there's fine-tuning or anything, because we should expect there to be life in the universe. If, for instance, the objective probabilities for what universes could exist entail that life-emitting ones are very, very unlikely, then this person has a very, very salient point, and I think fine-tuning would be established. So I think the argument, as you've put it, it's fine to pose on its own, but ultimately, whether it counts as a reason to believe in fine-tuning depends on what the probability distribution would be anyway.
Yeah, I see that. And I guess the reason I try to formulate it in non-probabilistic terms is because of this weakness of like, well, what does this even mean really, and how do you establish that? But so, like, suppose I said it this way, just to simplify things. Let's say in our completed physics, we say that there's 1,000 possible ways the universe could have been, and only one of them would have, or like does, I guess, allow for the existence of a complex life. So it seems that you could reasonably ask, why do we find that actually the one universe that allows for complex life pertains and the 999 others don't? Now, that is a question which doesn't use any probabilistic language. Now, I could turn that into an argument by saying this requires explanation. The best explanation is that God made it that way. Now, let's put aside the question of whether that's really a good explanation, but the point I want to make there is that that's a form of the fine-tuning argument that doesn't use any probabilistic language. So what would you say about that?
But don't you still feel that it kind of implies it? I mean,
well, maybe it does,
because if there's only one out of 1,000 universes, then this question seems pertinent, because in the back of your mind, I feel you've got the assumption that any of these 1,000 universes were equally probable. If instead this person asked the question, if we knew that there were 499 universes that were life emitting and one that wasn't, would this person's question be? Yeah. Would it be as interesting?
Exactly. Yeah.
And the answer,
it seems it wouldn't be. Yes.
It seems it wouldn't be. But the only reason it wouldn't be is because in your head you're assuming a probability distribution. You're assuming the principle of indifference. Really, that's what it seems to me.
I think that's probably true. There's just one caveat I would make, which is that we don't necessarily. Well, I don't think that one has to use probabilistic language or like the specific probability calculus in order to make statements about like plausibility and possibility and so forth, because you can make different assumptions and there are different formalisms for that. Now, whether that's going to be relevant here, I don't know. I think I may have mentioned this in the debate, actually.
I guess you could say that. Suppose we have this situation, then there's a fact. There'll be a fact of the matter. Either there is a probability distribution over these, or there isn't. If there is a probability distribution, then this question is only interesting if, and only entails fine tuning if the probability of a life-emitting universe is very, very low. But suppose that this argument isn't invoking any probability, and ultimately you have a set of possible universes, and there is no such thing as a probability distribution over them. Well, then what happens in that scenario? You're asking, why am I in this universe rather than the other 4,999? Or or however many other
Yeah.
ones you have. But if there's no probability distribution over these, then what really is the status of existence of them? Is the one you're in the only one that's actual? But how? But what? Why? What mechanism is what mechanism is actuality, and why has actuality picked out one universe and not three or all of them?
Well, I guess that's the question, right? And the idea would be, even if you don't want to use probabilistic language, you could still ask, why is it this way? And maybe you think that it requires explanation.
Yeah, and
you could just take that as a brute fact. Like, if there are many possibilities and one pertains, that requires explanation without using any probabilistic language there.
I think, in a way, this is the ultimate. This is the pinnacle of what we want to ask. Why is it this way rather than another way? If there are other possible ways, and my view, in the end, if we do want to ask this question, my view in the end would just be that possibility and actuality become meaningless, and
Interesting.
That everything. If we knew what was possible, if we knew all the possible universes there could be, knew all the possibilities, and the only thing that distinguished them was, and not phrasing this very well. Basically, the bottom line is that if something's possible, then I don't see why. If you've got a set of universes and all of them are possible, to me, a simple situation would just be to say that they are all actual. If at the end of the day, at the end of the road, you've got this set of universes and all of them are possible, and there's nothing to say that they're actual other than that you're in one and it feels actual, then what's the difference between possibility and actuality? Why on
channeling David Lewis here, modal realism?
I fully 100%. I mean, there's a difference between the philosophical possible worlds, because they don't rely so much on what's physically possible, and they in modal possible worlds you can say, oh, there's a possible world in which I play tennis, and you can say that, and that seems true, but it might not actually be true. I mean, these possible worlds might exist, and that might not actually be something that could actually happen. But say you got to the end of physics and the end of everything you could know about what possible universes are, and you've ended up with a final set of universes and that were all possible, then what is actuality anymore? Why, if there's no mechanism, if there's no further mechanism that picks out one of them to be actual, because if there was such a mechanism, surely that would factor into our physics, then surely you've just got to say they're all actual.
Yeah, well, that's a very deep question, which I'm going to put on the table for another time, because we're basically talking about the meaning of modality and possibility here, which is super interesting. And I mean, I think it is interesting to see how the discussion gets to questions like that fairly quickly. So we're running towards the end of time. I did want to leave a little bit of time to ask about multiverse. Now, I don't have a whole lot to say about multiverse theories other than I don't particularly like using them as a response, although I do think that they are a plausible response to people, to proponents of the fine-tuning argument. So maybe briefly, I'll just say Luke Barnes has a few things to say about it in his paper, but there's a few usual responses to multiverses. One is that they're speculative, which I don't actually think is a big problem, but I mean, yeah, I guess they are. Another, because like, is God not speculative? So that seems to be fairly facile as a response to me. But another response is that the multiverse itself would need to be fine-tuned to give rise to intelligent life, or to give rise to universes that have intelligent life. And that's related to, it's somewhat distinct, but a related objection, which is the Boltzmann brain objection. Basically, that if we have some multiverse, some universe generating process, that the universe we'd expect to find ourselves in, this is something you mentioned a bit before, would be a very small localized patch of order, possibly just a single brain that sort of fluctuates into existence and hallucinates everything that we see. And that these types of observers would be overwhelmingly more likely compared to observers in large and old universes like we take ourselves to be. And so this would seem to give rise to a new sort of fine-tuning problem as to why aren't we Boltzmann brains or something similar. What do you think about? So there's two questions there. What do you think about multiverse responses generally, and what about that Boltzmann brain response particularly?
I agree with you about multiverses, that it's not something I want to rely on. It is speculative, but as you say, that's not necessary. It's not necessarily a bad thing. But because they are speculative, it is something that when I talk about fine tuning arguments and when I talk with theists, it's not something I want to rely on and say this is where I'm gonna plant my flag. What I go for much more is the kind of probability. How, if you can't say that life-emitting universe is unlikely, then have you shown fine tuning in the sense that I care about? But if we ignore that, and we're happy that we'll avoid multiverses as our main arguments, we want to discuss them anyway. In physics, maybe it is. I think quite a few physicists and cosmologists are essentially. I think they think there's a sense of inevitability. I think in a way that eventually we are going to end up with some kind of multiverse. There are loads and loads and loads of different kinds you can have. You could have just isolated pockets of that are all spatiotemporally connected, but you could never travel to. You could get space-time generated through black holes. You could get other kinds of nucleations of universes within space-times. There's quantum kinds of many worlds. There's
not all of those will necessarily produce universes with different constants, though. Just
not necessarily, yeah. but a large class of them tend to do that. So there's all these sorts of multiverse models, and the reason we consider them is because they seem to come out naturally of the kinds of models and mechanisms that we've come out with. We haven't thought multiverses and tried to fit them to experimental data. It's much more been the case that we've got these theories that explain the work that are our best explanations for what's going on at the moment, and there are lots of them imply that you can have some multiverse structure of this kind. So I think, in my personal opinion, I think there's almost certainly a multiverse out there of some kind, and that the problems that we have at the moment in trying to work out what the nature of multiverses are is just because our current models of physics aren't advanced enough to do that yet. So a lot of the previous problems with inflating multiverses, which I think is one of the leading candidates, multiverse theories. The problem with inflating universes was this Boltzmann brain problem, that it seemed to be the case that if you had this eternal inflation, and then you ended up with, or it was far more likely that you'd be a Boltzmann brain, an isolated brain floating through space with a single flash of memory, than you would be ordinary observers like us. And so this is kind of in Barnes's paper, he calls it the principle of mediocrity. In any physical theory, in the theory of the multiverse, what we want is for our kind of life to be the expected kind of life. If it's not, then it's kind of, there seems to be a problem, because we've got this theory that predicts that we should have expected ourselves to be some totally different kind of life than the one we find ourselves in. And so you almost end up with a fine-tuning problem beyond that. But there was actually, but these problems with multiverses come because this is such a speculative area. We don't have any guides. We don't have any experimental guides to what a multiverse should look like, apart from we're just extrapolating the consequences of the theories that currently describe observations. So it is extrapolation. It is speculative, but a lot of the theories we're dealing with quite naturally allow for the existence of multiverses. And so in the long run, people will disagree. But to me, and I think a lot of cosmologists, it feels like multiverses are going to exist in some form. Touching on the Boltzmann brain problem again, I mean, this was a problem that's been around for a lot of multiverse models, but there was actually a very recent paper that was published, I think, only 2 or 3 weeks ago, and it considered a wider variety of phenomena that can happen in inflating universes, and found that if you took into account something known as uptunneling, which was kind of where small regions of universe start inflating and form new universes within your eternally inflating multiverse. If you include the effects of uptunneling and you also include the effects of black hole formation, then you could end up with the result that ordinary observers like us actually outnumber Boltzmann brains. And so this seems like a real possibility that the Boltzmann brain problem of eternal inflation could be somehow alleviated if we just knew a bit more about the physics of multiverses and the physics of the far future. These problems could well be alleviated. They're problems with multiverse models now, and they're problems that have to be overcome. But there's lots of ways that they could end up being fine.
Yeah, I actually think that's quite interesting. Well, I'd be interested to hear your thoughts about this. So I think the Boltzmann brain problem is an interesting problem, again, in its own right. And I, as you said, I've seen other models of this that say different things. So it's an active area of research. But the more fundamental point that I would just make is that the naturalist, or the person responding to the fine-tuning argument, at this point, we've moved from, we think that fine-tuning is maybe an issue. We're going to try to explain it. The postulated explanation is that there's a multitude of universes that have different constants, and by observer selection effect, we find ourselves in the one that allows our existence. That's the postulate. Now, we don't need to have a physical theory of that, unless there's a better theory on the table that the proponents of the fine-tuning argument have, which is better than ours. But they don't have that. They've got a metaphysical hypothesis, which is God. So I don't, and this is, Oppie makes this point a lot. It's like, well, if you're allowed to have a metaphysical hypothesis, I can have a metaphysical hypothesis. So I don't need any physical model, whatever. I just say, look, there's a series of these different universes that give rise to, that have different constants, and that's all there is to it, right? That's just a hypothesis. I don't actually see what's wrong with that. Again, that's not my preferred response, but yeah, I just don't see what's wrong with that philosophically speaking. Well, what do you think?
Yeah, I think I agree entirely. Because it is speculative, you don't want to base your argument on it. But I mean, as a physicist and as someone who thinks about these issues, you do have to think, what do you think is the most likely speculative hypothesis? Where do you think things are going? And thinking multiverses, while there are problems with them at the moment, thinking that multiverses may well end up being the solution, it seems better supported than having the much more metaphysical claim that a God exists, and a God chose this particular chemistry and this particular way of structuring the universe, when the multiverse theory comes out quite naturally of theories that we already know. The multiverse theory itself is speculative, but the reason we think about it and the reason we're investigating it is because it seems a natural consequence of laws that we do have very good verification. We do have good evidence and good verification for, whereas you don't have that. Or I'm sure Theus will disagree, but certainly from my perspective, I don't think there's nothing like that for God.
Well, yeah, I mean, I agree with that as well, but obviously that raises further questions. So one thing there's a couple of points to chat that I wanted to raise, and then we'll wrap up in a little bit. But I wanted to ask this because you said something before, which I've heard other physicists or people from a physics background say, which is that it looks like there's lots of different avenues where we might end up with a multiverse. I think Sean Carroll might have said a multiverse is inevitable or something along those lines. And maybe he's simplifying a bit when he's talking in those terms. But what I find interesting about these sorts of statements is that not that I necessarily disagree, but it seems to be interpreting physical models these statements seem to be interpreting physical models in a very particular way. So if I'm an instrumentalist, right, yeah, I'm going to say that physical models, like physical theories, are used for their predictive value, and that I don't necessarily place any ontological interpretation on them. And so to say that our physics seem to be moving in the direction of a multiverse, like, I don't even know, it's not clear what that would even mean under an instrumentalist position, unless that had particular, like, testable or pragmatic implications. Now, maybe it would at some point. Maybe we get to the point where a a model that has a multiverse in it in some sense would be, predictively better than a different one. But even there, the question would be like, well, does that mean that there actually are multiverses? And the instrumentalist would either say no, or they would just say, well, we have no idea, or can't answer that question, something like that. And just to sort of clarify that question a bit more before I let you respond, I would say that today we still really do not know how to properly interpret quantum mechanics and quantum field theory. I just mentioned that a little bit earlier about the ontology of these two theories. That's still hotly debated, and it's sort of unclear exactly what they mean about like the way that world really is. So I'm just interested in your perspective there. Like, I don't know, how are physicists thinking when they say things like, well, it seems like we're going to get a multiverse, when that's based on sort of extrapolating theories, and then it seems to me at least interpreting them in a particular way. I'm just sort of interested what you think about that.
Yeah, no, I think this kind of view, and it's certainly true of myself, it comes from a very realist interpretation of physics and of science in general. It's if when we say that we think multiverses look inevitable, what we're saying is that when we get a higher theory of physics, we think that some of the objects in that theory are going to be are going to be other universes, or at least that this underlying mathematical framework permits the existence of and offers mechanisms for the generation of multiple universes. There's a funny so in the quantum theory of many worlds, I was taught a lot of interpretation of quantum by Simon Saunders at Oxford, who's very involved with this and a big Everettian, very in favor of many worlds. And when I asked him what kind of is the evidence for many worlds, there's lots of good theoretical reasons, but a kind of one way of summing it up is, or one kind of cheeky way of summarizing it is just to say, well, because the world is described by quantum mechanics. The evidence for many worlds is that it's described by quantum mechanics. And I think, and
in quantum mechanics you have basically the appearance of many worlds, and that's what Sean Carroll says, that, well, you've got these different states in quantum mechanics, so like, why think one of them's real but the others aren't? If
our universe wasn't described by quantum mechanics, then yeah, sure, there aren't many worlds, but it is. So
I think, oh, sorry.
So one could respond to this by saying, well, there are other interpretations of quantum mechanics, so surely you could just adopt an interpretation that doesn't have many worlds. But this isn't quite true. There are lots of interpretations of quantum mechanics, but a lot of them are experimentally different. They're just not experimentally different at the level that we can test.
Yes.
So there's dynamical collapse models, which provide dynamical mechanisms for wave function collapse, but they have certain parameters and they entail things that would be experimentally testable. As far as I know, I might be wrong here, but as far as I know, the only two interpretations of quantum mechanics that are identical in what they predict are many worlds, and which doesn't alter quantum theory at all, and the pilot wave interpretation. But what many worlds theorists would say about the pilot interpretation is that a pilot wave theorist is just a many worlder in disguise.
Well, that's what they say.
And there is kind of good reason, but my point was really just to say that you can't just interpret quantum mechanics however you like. If you want to interpret it in certain ways, then it does actually change what's predicted, and these changes will be experimentally verifiable. So in a sense, the many worlds theory is, I think rightly, some will disagree, but I think is rightly the pure interpretation of quantum mechanics without any additions, without any. Yeah, there we go. Exactly what's said there.
Sorry.
That's the point that many world theorists want to make. It's the model that just takes the maths at face value.
Yeah, and I mean, again, this is a little bit. The reason I asked about this is just because this sort of similar type of argument appears to be used with respect to talking about, say, multiverses. And I actually think this is a mistake, even though I myself am a realist. I think you have to be very careful about what parts of the theory you take as ontologically committing. And I think it's completely wrong to just say, like, every part of the mathematical structure is ontologically committing. This is where I think that, like, the idea of taking the math the most seriously, it just, I don't even know what that means, really. It just seems a bit odd. But anyway, that's a whole other discussion to have. I just thought it was an interesting thing that I'd ask about. I mean, I think physicists are also not often inconsistent there, because when you ask them some questions, they'll talk about physics as if it's like as if they're a realist. If you ask them different questions, they'll talk about it as if they're instrumentalists. Not all physicists, obviously, but I've seen this happen.
I'm a big realist in that sense. So I just feel like if you hypothetically, if you reach this final theory, and it predicted everything perfectly in this mathematical framework, and we couldn't find any simpler or better mathematical framework, then to me it seems like whatever mathematical entities that appear in this theory are what exist.
Interesting. Well, we'll have to schedule that for another time, because I think that's a very important discussion. So there's a couple of things from chat I wanted to highlight. We've got a donation here from Camille. I think that's about $5. So thanks very much, Camille. Camille asks, what does Matt think about fine-tuning being metaphysically necessary? Isn't that more parsimonious than fine-tuning plus God being necessary? What do you think about that, Matt?
So I need to see that a bit longer.
Oh, sorry. I'll leave it up.
Being metaphysically necessary. Isn't that more...
So this is the Gray-Moppy argument, right? That our universe is just necessary. Metaphysically.
So this kind of comes down to what I was saying in terms of possible worlds. To me personally, I think it is parsimonious if you do have a set of possible worlds that you just say that all of them are necessary. In the fact of their existence, they all necessarily exist because they're possible. This isn't a very standard view, I admit. But
yeah.
But for me, to put it more into perspective of the way these discussions usually go, possibility for me is differences between possible worlds. Something is necessary. Something usually, if it's in a world, it's necessary if it exists in all possible worlds.
Yes.
But the existence of actual worlds, that's not something that you can really address with this notion of possibility and necessity.
Well, there's usually only one actual world. That's the world we live in, is the usual idea.
So I take a very David Lewis line on this and think, well, actually, putting this idea of actuality seems to me to be putting extra structure on.
Interesting.
And so it seems to me much more parsimonious just to say they all exist, and necessarily is kind of a tautology when applied to that. But so I think with respect to fine tuning, I think if there were a set of possible universes, I think it would just be, to me it seems more likely, more parsimonious to say that they all just exist.
Yeah, that's a bit different to the argument that David Lewis, as far as I know, gives for modal realism, which is that it's basically an indispensability argument for talk about possible worlds. So basically, they're so useful that just as other things that are useful we think refer to something real, then, well, possible worlds must refer to something real, so they must exist. I think he would still say there's one, as far as I understand, he says there's one actual world, but all of the other worlds are also real. They're just not actual because, well, like, we're not in them. But also, William Lane Craig, my buddy, he actually thinks something similar to this, or at least it seems to be the case that he does, because Craig thinks that he's a presentist, so he thinks that only the present exists, but he also thinks that the past is real. And I talk about this in the video we did on the Kalam with Nathan, and in my book as well. So it's a bit hard for me to understand what he means by that, but there
Nobody
are
understands what he means by that.
Well,
I certainly don't.
So Alex Melpass actually mentioned that modal realism could be a model for understanding that, in terms of things being real but not actual. Although I don't actually think Craig would want to go there, but I just thought I'd mention it because I think it's interesting. But I don't want to get on philosophy of time now. We'll have to talk about that another time. But anything else you want to comment on that?
I think the bottom line is that just if you got to that stage that you knew what all the possible worlds are, then adding this idea of actuality just seems unnecessary.
Interesting.
I think there is a kind of physicist / mathematician analog of David Lewis. I don't know if you've read much Max Tegmark.
Oh yeah, a little bit.
Yeah, so his grand idea really is, I guess this probably was a big inspiration for me, really, a big influence on me, really. His big idea was that at the end of the day, physics as we know it is going to be a particular mathematical system, and then there's going to be a large class of there's probably a large class of consistent mathematical systems, and all this existence possibility doesn't matter anymore. What exists are all these mathematical systems, and we happen to find ourselves in one of them. I think that's kind of the approach that's most informed my thinking, because it seems to get rid of all these worries about possibility and actuality and things that to me don't seem physically meaningful.
That's so fascinating, because I think about things so differently to that. But I don't want to get into that now, because we need to wrap up pretty shortly. But we'll have to get you back, and we'll talk about more of this stuff. I did want to spend. So we haven't really talked much about the God hypothesis here. We've mentioned it. Obviously, we can't get into details here, and we're probably not going to disagree too much. But it would be remiss of me not to allow a few minutes to talk about this. So my position is that I'm not convinced the universe is fine-tuned globally, in the sense that overall in the parameter space, the number of combinations that allow for any type of complex life is low. I admit that there's local fine-tuning. Matt disagrees about that. That's fine. But even if we did establish global fine-tuning, I think that the God hypothesis is a very bad explanation for that. And in my debate with Luke, as well as, actually, I don't talk about this as much in my book, but I did discuss this in my debate with Luke Barnes. I give some of the reasons for that. And basically, the bottom line of it is, it seems to me that God doesn't really rule anything out. We don't know what God wants, or because he's capable of anything. Everything you want to say, every prediction you want to make about God, it seems to me you have to postulate some new desire or property or purpose or whatever of God, and that your theory is going to be basically just as complex as what you're trying to explain. That's the short version of it. So because of that, I think God's a very bad explanation. Do you agree with that? Disagree? Or what's your view on that?
It's funny, isn't it? Because this is the criticism that's usually railed against multiverse theories. It doesn't rule anything out. Everything that's possible happens. In my personal view, that's not a problem, because I think I think it's most likely that everything that does does happen and is real. But that's very much my side of things. But that's the criticism they rail against multiverse theories, but it seems equally applicable to God. I mean, if God really is not bound by anything, there are no independent laws of logic or possibility, then everything flows from God, and he can make any laws of logic he likes, any laws of chemistry, any laws of physics, anything whatsoever. And it rules out even less than my view, which is that everything that's possible. Because what's possible for me isn't everything. Anything that falls foul of the law of contradiction is impossible, and things like that. Whereas on a God hypothesis, any logics are possible. Any set of anything's possible.
Well, yeah, I mean, my favorite paper on this is Electrons in Love, which discusses the idea that God could make, if he wanted to, electrons that can fall in love when they bounce off each other or whatever, because he's God and he can make stuff like that as long as there's no sort of contradiction there. So there's actually a much wider space of possibilities that are equally consistent with God's existence. So I don't think it's a good explanation there. But it's interesting that this notion of what constitutes a good explanation came up very prominently in my debate with Inspiring Philosophy. I don't know if you saw that, Matt, but that was focusing on his digital physics argument. Yeah, well, he appeals to lots of physics, which you probably find as annoying as I do, because I think a lot of it's misinterpreted.
I need to watch that debate, because that's something I should.
There's not as much physics in that, actually. It's mostly the philosophy side. But I did a follow-up video talking about some more of the physics, and you could probably add stuff to that I didn't pick up as well. But anyway, the point is that in that debate we talked a lot about what makes a good explanation, and I mean, that itself is disputed, but my main contention is that an explanation is supposed to say why this and not that, at least like probabilistically, at least why is this more likely, not that. And God doesn't seem to do that for me, unless you invoke a theology, which then you're just adding to the complexity of the postulate. Whereas I think a good explanation, like a naturalistic explanation, is able to rule out and the better the explanation is, the more things it rules out, as long as it's consistent with what we actually observe. Now, I think actually multiverse theory is very interesting because they actually, as you say, they don't really rule out things, or at least it's not clear that that framework works in the same way. So that's an interesting discussion to have as well, what an explanation even looks like in that space. That's one of the reasons that I'm not a fan of multiverse or Everettian quantum interpretations or other multiverse theories. Not so much about that they could exist. It's more like why we would think that they exist, because I don't think they're actually explanatorily very useful. But again, that's going to depend on your theory about what makes a good explanation. So any thoughts on that, or maybe sort of general summarizing thoughts?
I think at some point, while at the moment when we're looking at our world, we want to rule things out, and we want an explanation that that properly explains what we see around us and rules out a lot of the things we don't. At some point, you're going to get to some theory where there's things, unless there is one consistent theory and that's it, in which case what we see was what we were always going to see. But I think most people think that's unlikely. If you end up at the pinnacle and you find that there's lots of different possibilities, then I mean, how could you rule them out? Whatever explanation the explanation that you have, if it allows for these possibilities that aren't things that we see, then at some stage you just got to accept that. And I think that the multiverse kind of is that stage. At some stage, if our laws of physics kind of look like they entail a multiverse where there's a small set of parameters maybe that take different values in different universes, well, then maybe that is the level. That is the highest level we get to. And maybe if there are other universes, if there are other possible universes and they do exist, then we're going to get to that stage at some point where we can't rule everything out.
Yeah, and part of this relates, I think, back to what is the point of an explanation, and what's that doing for you epistemically? Yeah, and that's a whole host of issues we can't get into here. I think that explanations serve the reason I think that they're useful is I think that they serve an important epistemic function in theory selection, basically. And what we should be doing is trying to pick the theories that explain the most with the least postulates, so that are the best theories, essentially. And you may at the end of the day end up with some brute facts at the end of the day that just don't have any further explanation. But that's your best. The theory that does best on those sort of measures is your best guess about what reality looks like. But then, of course, we have to ask questions about like how to evaluate supernatural beings like God, and how to evaluate multiverses. So there's other cases like this that maybe are a bit difficult, or at least are quite contentious about how to evaluate them. So I think that that's actually the basis of a lot of these disagreements here. Anyway, sorry, you were going to say something?
No. I think the multiverse is because you couldn't. There's a sense in which you couldn't even, in principle, test it or experiment with it. That's what worries people. But if it's there, then it's there. So,
well, yeah, but then that comes back to the question: how would you know it's there? And
exactly.
Anyway, so
but yeah,
we go around the circle. But yeah, so thanks very much for coming on, Matt. Any final remarks you wanted to make about the fine tuning argument or anything we've discussed?
First of all, thank you very much for having me on. It's been really great. It's been great to be on the channel, and it's been a great discussion. I think what we've said. What we've said certainly does not sum up everything, because 2 hours 2 hours is hardly a summary. But I think the bottom line with fine tuning is that we have absolutely no idea whether the kind of universe we see around us, and whether life-permitting universes in general are what we should expect to see or what we shouldn't. And until you have good reasons to suspect that this isn't what we should expect to see, then I don't think the fine-tuning argument can be taken. It can't be taken too far.
Yeah, and I don't fundamentally disagree with that. I think that we're a bit. Well, I don't think we're too far apart, even though we do have some points of disagreement. But it was also just good from my perspective to hash out some of these ideas and talk to someone who has more of a physics background as well to see what you think. So I think from my point of view, I still think that I'm right about the point that we don't really know whether the universe is globally fine-tuned. However, I take epistemic disagreement pretty seriously. So I think I need to be quite careful in how I use that, because many people aren't convinced of that on both sides of the aisle. So I don't think it would be enough to rely on that, even though I'm going to keep pushing that in the discourse, because I think it is underexplored. But so we did talk about the issue of whether the universe is globally fine-tuned, in the sense that in parameter space, the range of values that would permit complex life is small. We then talked about the issue of how you establish the probability distribution over the parameter space, and what that might even mean, and how you establish it's unlikely that we would see what we do, or whether that makes sense. And then at the end, a little bit, we talked about possible explanations for fine-tuning if it is indeed unlikely, including the multiverse and a little bit about God. And so, yeah, I'm not convinced the universe is fine-tuned, but I mean, even if that was established, I do not think God is a good explanation for it at all. And I think
I agree with you there.
that is also an unappreciated aspect of the argument. For example, Robin Collins doesn't talk about this much. And when I asked him about this in the debate, Luke Barnes basically he had a few things to say. I don't want to strawman him, but he did repeatedly say, I'm just going to refer to philosophers on that. I think he mentioned Swinburne. So well, I don't know. I just felt that was a little bit dodgy. If you're making an argument, then I think you should make the whole argument and not sort of pass the ball at that. But again, he didn't completely do that, but he was a bit, it wasn't very committal on exactly what he was claiming there. It was just like, well, it could be this, which I felt was a bit wishy-washy if you're presenting an argument. But anyway, I didn't mean to go down that road. So yeah, hopefully people found this interesting. Again, thanks very much, Matt, for coming on. And I encourage people to check out his channel. Anything you want to say about your channel in closing to plug that?
It's very, very shortened versions of things that get discussed here, looking at the kind of standardly peddled arguments for God and discussing them in the light of science and the physics that I know, and discussing how convincing they really are. Spoiler, I don't think they are, but there's more interesting things to be said there.
Awesome. Well, thanks again, and thanks everyone for coming along and listening. And I was going to say something else. Oh yes, one more advertisement. So the next video that I'll be involved in will be a discussion with Nathan from Digital Gnosis, looking at the argument from reason. So that will be Sunday my time. So if you look on Digital Gnosis channel, you'll see a link to that. And so yeah, you can check me out there. And otherwise, I guess I'll see you around.
See ya. Thank you very much.
Thanks, everyone.